Okay, so we continue to study Cauchy sequences, and now let me formulate. This is theorem 3 of our section about limit in Rn. So let me formulate it like that. That is Cauchy criterion in Rn, and it sounds like that. A sequence x, n, m in Rn converges if and only if it is a Cauchy sequence. Proof. First part will be converges, hence Cauchy sequence. And this is valid in arbitrary metric space. So I'll prove it just in a metric space. So what we have? We have that there is a limit m tends to infinity of xm, let it be x naught, and that is in a metric space. And what it means? It means that for arbitrary epsilon greater than 0, there exists a number n such that for all m greater this number, we have an equality rho of xm to x naught less than epsilon. Recall, I consider a metric space. Now, since this is valid for arbitrary epsilon, I would like to take epsilon over 2 instead of epsilon here. This is also arbitrary positive number. Then, for arbitrary m greater than n, and for arbitrary just that m, and for arbitrary natural p, we have the following chain of inequalities. Distance between m plus p and xm, according to the triangle inequality less or equal distance from xm plus p to x naught plus distance from x naught to xm. And you see that for arbitrary natural p, m plus p is greater than capital M. Hence, both terms here are less than epsilon over 2, and we have epsilon as a result. And what is underlined is precisely definition of a Cauchy sequence. So it means we have proved in this side. So let me once again note that this was proved for an arbitrary metric space. Now we proceed to reverse part, and that is the proof is valid just for Rn. So Rn. Now suppose that we have a Cauchy sequence is a Cauchy sequence in Rn. What it means, let me recall what is the definition. For arbitrary epsilon greater than 0, there exists a number, natural, such that for all m greater than this number and for all natural p, we have an equality norm of xm plus p minus xm is less than epsilon. Now what is norm? Norm in Rn, xm plus p minus xm, is equal by the definition to square root of squares of coordinates of this vector. So x m plus p 1 minus x m 1 squared plus so on plus x m plus p n minus x m n squared. So we take here xm equals to xm1 so on xmn. So I denote coordinates by extra index, second index, which varies from 1 up to n. So we have n coordinates for each vector xn. Now look, we have this norm is less than epsilon, and if this square root is less than epsilon, then of course every modulus here is also less than epsilon, right? Because we add something non-negative to each of those modulus. Hence, what we deduce? We deduce for arbitrary j from 1 up to n, what we have. Oh, maybe, in fact, maybe I'll put this quantum a little bit later. It is more convenient. So for arbitrary epsilon now, we found a number n such that for all m greater than n and for all p natural, we have for all j from 1 up to little n, we have an equality modulus of x m plus p j minus x m j less than epsilon. So if I fix arbitrary j and look at everything else, then we recognize immediately the definition of Cauchy sequence of numbers. So what is underlined means that the sequence mj, m from 1 up to infinity in R, is a Cauchy sequence. For all j from 1 up to n. So we have n Cauchy sequences. Now, as we know from the first semester, if a sequence is a Cauchy sequence, then it converges. So there exists a limit which I may denote by x not j, which is equal to the limit, right? J tends to m tends to infinity, x m j. So each of those sequences has a limit, j from 1 up to n. Now we apply lemma from former lecture, which says that a sequence in Rn converges if and only if each of coordinates converge. So we have n sequences and coordinate sequences, each of them converge. Hence, we obtain that the limit of the sequence of vectors is equal to x naught, which is vector with coordinates x naught 1, so on, x naught n. This vector is by definition that one, x naught. And it means the theorem is proved. We have proved that our Cauchy sequence converges. Okay. Maybe it's a good time to make a series of definitions. So, look. You see, in one side, we have an assertion is valid for arbitrary metric space, but another side, not. So, it gives it gives a sense to make a definition, the following definition. So, definition. If an arbitrary Cauchy sequence xm in a metric space x converges, then x is called a complete metric space. Of course, this definition automatically gives what a complete normed linear space, Euclidean space, and so on, but they have special names. So, next, a complete normed linear space is called a Banach space. Banach space. And a complete Euclidean space is called a Hilbert space. These are main objects for function analysis. We will study it a little bit in the last semester of analysis, 5th semester, so next year. And now I'll not go more deeply into details for those spaces. And okay, next theorem, let us study more precisely notions which were introduced before. And now we can connect the notion of closed set with limit. So, and that theorem may be called criterion for completeness of a set. Sorry, closedness of a set. So a set E in a metric space, X is closed if and only if from the following supposition. So if we suppose we have a sequence in E and that sequence converges to something, follows X naught belongs to E. So closedness is equivalent that the set contains all possible limits of its sequences. Once you have a sequence of points of your set, and this sequence has a limit, then the limit belongs to the set also. And in other words, it's the same in fact. So equivalent reformulation, let me write like that, equivalently X naught belongs to the closure of a set. Closure. If and only if there is a sequence Xm such that the limit of this sequence equals to X naught. So the closure consists of all possible limits of sequences of our set E. So proof. So what we have to prove in fact for both assertions is to consider all adherent points. So suppose X naught is an adherent point of E. So what it means? It means that for arbitrary epsilon greater than 0, there is such an intersection is not empty. That is the definition of an adherent point, right? Now, if so, we can construct now a sequence which has a limit at x0. How? Look, for example, put epsilon equals to 1. Then, as we know, there is a point in this intersection, right? Let me denote x1 belongs to this intersection, which is not empty by supposition, right? Epsilon equals to 1, so u1 I can write here. Then we can take epsilon 1/2, it gives a point x2, and we can continue so on. Epsilon 1/m gives a point xm in this intersection. So we continue up to infinity. Hence, we construct a sequence of points xm in E, right? A sequence of points xm in E, because all of them belongs to E. Also, we have that distance from xm to x0 by the construction is less than 1/m. Hence, this sequence, limit as m tends to infinity of xm, equals to x0. So what it means? It means we have constructed such a sequence for arbitrary adherent point, right? And of course, vice versa, if we have a point x0, which is a limit of a sequence, what it means if we have this one. Now, suppose we have this one. Then what it means? For arbitrary epsilon greater than 0, we have an index n such that for all m greater than this n, we have distance between xm and x0 is less than epsilon. And what it means? It means that all those points xm belong to the epsilon neighborhood, right? And it means that this intersection is not empty. So from this equality, if x0 is a limit of a sequence from E, follows immediately that x0 is an adherent point. So every x0 which is a limit like here, is automatically is an adherent point, right? And what is here? It means that all our set E contains all adherent points. Means it's closed. Okay. That's it. And if it's closed, it coincides with its closure. That is why those assertions, in fact, are equivalent. Okay, this was about closedness, which is characterized with the help of the limit notion. Next, very important notion is compactness. So, let me give a series of definitions. Not a series, just one definition. A set, capital K, in a metric space is called compact if for an arbitrary, not for, if an arbitrary covering of K by open sets G alpha. So what means covering? Means that union of all those open sets contains capital K. If an arbitrary covering of K by open sets contains a finite subcovering. What it means? There exist finitely many numbers, let's say alpha 1, okay, finitely many subset of capital A. A is a set of indices. I don't know how many, usually infinitely many, of course, open sets we have, such that union of those open sets still cover capital K. So that is subcovering. So you see, this definition contains, in fact, several definitions inside. I mean, covering, subcovering. What is it? So covering means that collection of our sets cover the whole set, capital K, right? And subcovering means we have finite subcovering, finitely many of those sets, and they still cover our set. And now, next theorem, next two theorems, in fact, they are valid for an arbitrary metric space, and they give an impression about main properties of compact sets. So, theorem 5, in fact, the name for that theorem is practically coincides with the theorem itself, so it makes no sense to call it somehow. So, a compact set in a metric space is closed. Proof. So, how to prove it. Let me call. Yeah. So let me denote. Let K be the compact set and in the metric space X. So how to prove that capital K is closed? We know from the first series of theorems that K is closed if and only if its complement X minus K is open. So I want to prove that one. So it means I want to prove that arbitrary point for this set is an inner point. So what it means? X minus K is open means that arbitrary X in this complement is an inner point of X minus K. That is what I want to prove. So let me do it. Take arbitrary, once again, I want to prove that arbitrary point of a complement is an inner point, right? So I take X and I fix it arbitrarily, right? Now, take any point Y in capital K. There are two neighborhoods let me say U are Y of X and U are Y of Y such that they don't intersect. So the intersection is empty. And in fact, what is Ry here? Ry is just, let's say, half of the distance between X and Y. So let me give a picture. There are two questions. Sorry, I need to answer. First question: why rho of xm x naught is less than 1 over m? Here, those points were chosen this way, right? We choose them because the intersection is not empty, so we choose point xm just in 1 over m neighborhood. Since this is not empty, then we choose xm in that neighborhood. And xm is in this neighborhood automatically means this inequality by the definition of the neighborhood. That is why. And what is capital A in the definition of covering? So, doesn't matter. Capital A here is some set of indices. I don't know which set. This is usually infinite set, and moreover it may be not even natural numbers, maybe real numbers, maybe some. Doesn't matter. In fact, just now you will see what it can be. So, set of indices, that's all. Somehow we, so we have many sets, right? And I should indicate them somehow, right? I indicate them with the help of some indices which belong to a set of indices. That's all. So, how many sets doesn't matter. Absolutely not important. Okay. And you see just now the example of a huge set of indices. So look, if I have two different points, right, of a matrix space, we have a distance between them, right, and we have non-intersecting neighborhood of 1/2 of distance. For sure, they don't intersect because for a point in intersection, we have simultaneously inequalities distance less than this ry, what's impossible. Okay, so we have not intersecting neighborhoods. Now, look, I have made that construction for arbitrary point y in capital K, right? Arbitrary. Now, that is an example of very strange indexing of those open sets. So, union for all y in K of those u ry of y contains K. So we have an open covering now. Why? Because, look, for sure, this neighborhood, here we have positive, right? Positive number. This neighborhood contains the point y itself. And we have union of all such neighborhoods for each point of capital K. For sure, every point of K belongs. So we have, if we consider arbitrary point of capital K, then it belongs to neighborhood with center at this point, right? So this union for sure contains capital K. And that is an example of this capital A, right? So numbering is just by points of our sets, That is one way. Doesn't matter how many sets we have, Infinitely many, and you know, the set of real numbers is continuum. So we have essentially more points in real than in the set of natural numbers, and in fact it may be even larger. Doesn't matter. Absolutely not important. Okay, let's have a break. We have open sets, and altogether they cover our set. So it means we have an open covering. And since capital K is compact, by the definition of compact, there exists finite subcovering. So there exist finitely many points, let's say y1, so on, y capital N in capital K, such that the union of R yi of yi still contains capital K. So we had open covering, we can choose finite subcover, finitely many. That's important. Why? Because now put rho minimum of ry1 so on ry capital N. So now we have finitely many positive numbers. Of course, finitely many positive numbers, we can find a minimal number of them, right? And now look at u rho of yi. That is a neighborhood of yi with radius less than ryi, less or equal, right? Hence, this is a subset. This is a subset, right? For arbitrary I. From 1 up to capital N. Now, how we constructed those neighborhoods? Recall the construction. So we choose this ry how in such a way that the intersection between neighborhoods of y and of x with this radius is empty. So it means that the intersection of u rho of yi with u rho of x is empty. Because of course also u rho of x is a subset of all u r y I of x. That is also true, because radius is less or equal, right? Look, so if neighborhoods with larger radius did not intersect and we consider smaller radius, then of course they do not intersect either, right? Now look. So u rho of x has no intersections with in fact also what I need that I need more. I need also that u rho of x has no intersection with u r y I. That is what I need. That is what I need. That is not important. That is important. That is important. Is empty. That is empty. Yeah. So in fact, if this is x, this is yi, I am not interested in that one. That is not. I am interested in this one. That is yi. I am interested only in that neighborhood. Why? So this neighborhood has no intersection with that one. Now, it follows that this neighborhood has no intersection with union of those neighborhoods. Is empty. So why? If it has no intersections with each of them, then it has no intersection with union, right? Then we know that union of those neighborhoods contains our set capital K. The intersection is empty, so the intersection of u rho of x with capital K is also empty. And what it means? It means that u rho of x is a subset of x minus K complement of capital K. So let me go back. We took arbitrary point in the complement, and we have found a neighborhood of this point which is also in the complement. It means that the point x is an inner point. So is an inner point, hence this set is open, and finally our set capital K is closed. We go back on this chain of implications. Okay, the theorem is proved. Next theorem, also it can be named by itself, right? A closed subset of a compact set is compact. Proof. So let F be a closed subset of compact capital K. We want to prove that capital F is compact. So we need to prove that for arbitrary covering of F by open sets, we can find a finite subcovering. So take arbitrary covering of capital F by open sets J alpha. So union of all those sets J alpha contains F. But F is closed. Closed means, so F closed, hence complement is open. So it follows that the following collection of sets together with x minus F contains capital K. Because look, this thing contains F, right? And we added everything else. So for sure we cover everything in fact. It covers the whole space, hence it covers capital K. So, but now look, open, each of them open, right? So we have a covering of capital K by open sets. But capital K is compact, hence it contains a finite. Okay, look, what is finite? It might be so that there exists alpha 1 so on alpha n such that union of j alpha I together with x minus f covers k as well, right? That is subcovering. Maybe this is not included, maybe this is enough, right? But if this is valid, this is true, then we don't need to prove anything, right? Because k contains f, right? So if nothing is here, right, then we have finite subcovering. But if this should be included to cover the whole capital K, then what we observe? Look, x minus f has no intersection with f, right? So if this covers f, then what follows? We can deduce that the union of G alpha I covers f, right? Because this extra set doesn't have any intersection with capital F. So, for arbitrary covering by open sets, we have found finite subcover. That's all. So, closed subset of a compact set is compact. Now, for the set Rn, there is very important example of compact set definition. N-dimensional cube is the following thing. Cartesian product of segments with lengths are the same, where lengths are the same. So cube is Cartesian product of intervals of the same length. So n equals to 2, what is it? Cube in R2. Square, of course, right? Yeah. In R3, usual cube, and okay, sometimes for n equals to 4 it is called hypercube, but we use the same word. It doesn't matter how many dimensions. And now very important theorem for us, theorem 7. N-dimensional cube is compact in Rn. So every cube is a compact set. And after that, look, before to prove, let me observe several consequences. Look at that theorem. Every closed subset of a compact is compact. So it means once you have bounded closed set, what is bounded? You can find a cube which contains this set, right? And closed subset of a compact is compact. So every bounded closed set is automatically compact. That's very important corollary, but we'll prove it later with characterization of compact sets in Rn. So proof. By contradiction. But what is contradiction here? For a while, we have only one characterization of a compact set, by definition, right? So, by definition, what is compact? For arbitrary covering by open sets, by open sets, for arbitrary covering by open sets, we can find a finite subcover. Now we suppose that is not true. It means what? We can find a covering by open sets. So let collection J alpha and A be a covering of cube capital I equals to product AI BI of the cube of the cube. Let B a covering. Let J alpha be a covering of the cube such that, of course, every J alpha are open, right? Are open, be a covering such that I cannot be covered by any finite collection of J alpha. So no finite subcovering. So it means if we try to choose finitely many sets, doesn't matter how many, but finitely many. That's important. If we try to choose finitely many sets, then we cannot cover this. That is our supposition. So cube is not compact. Okay, now the idea is the following. Look, let me draw a picture. Maybe, no, here. No. For R2, we have our cube, which is square here, right? And let us divide every edge of our cube by 2. If we divide every edge by 2, what we obtain? For R2, we obtain 4 squared, right? For R3, how many cubes we'll obtain after this splitting into equal pieces? 8. So in general, for Rn, how many? 2 to the power n, yes, precisely. So divide every edge of I into halves to obtain 2 power n equal cubes with length of the edge. What is length of the edge? Equal to d over 2, right? We divide by 2, right? So we have finitely many. Look, we had a cube, and we split it, and we obtained finitely many smaller cubes, right? But we suppose that doesn't matter how you choose finite collection of G alpha, you cannot cover the whole set, right? It means that there is at least one of those smaller cubes. So they exist. They exist. At least one of smaller cubes, right? Let it be, I'll denote it by I1. Let it be I1. Which cannot be covered by any finite collection of G alpha. Because if you could cover each of them by finitely many, right? Then you have finitely many cubes. Each of them is covered by finitely many, right? It means altogether you have finitely many. So at least one cannot be covered by finitely many. Right? And we continue. We continue this process, right? We continue this process. So as a result, continue the process of dividing edges in halves, right? So we divide edges in halves, and automatically every time we divide the cube into 2 to the power n cubes, right? And every time when you do it, you have finitely many cubes, and at least one of them is not covered by finitely many sets G alpha, right? So you continue. We obtain a sequence of cubes. I contains alpha 1, alpha 2, so on, right? I am equals to, let's say, A alpha m d I m, and what we know, length for each cube is what? G over what? 2 to the power m, right? 2 to the power m. Every time we divide by 2, right? So we have smaller and smaller lengths. And each of IM cannot be covered by finitely many of G alpha, right? That is our construction. So we have a sequence of embedded cubes. Look at every dimension. So for example, look at dimension here, right? So here we have A1, B1, right? So next will be A2 here. Okay, if this is just axis, then A2, B2, right? Next, A3, B3, and so on, right? So, in every dimension, we have a sequence of embedded intervals, right? So, for every dimension, we have a sequence of intervals, nested intervals, right? Nested intervals, we call them. Nested intervals. So, let's say AI BI contains AI1 BI1, AI2 BI2, and so on, right? And you see, lengths tend to 0, right? But in fact, for non-empty intersection, we don't need to suppose that lengths tend to 0. So, from the first semester, we know there exists a point C, I, which belongs to the intersection of all those nested intervals, right? And that can be done for every dimension. That can be done for every dimension. Hence, as a result, we constructed a point C, which belongs to the intersection of all cubes, right? So somewhere here, there exists, we continue that process and we obtain a point of intersection somewhere there, right? C, let's say. That is a point of intersection of nested cubes. Nested cubes now, right? So, but this intersection for sure is in our set original cube I, right? And as we know, from the beginning, we had a covering of I. Covering means the union contains the whole cube, right? So, hence, there exists alpha, let's say alpha naught in A, such that J alpha naught contains our point. So, the whole collection, there is a question, can cubes intersect each other? They will not intersect. Every time, by definition, we took, so we divide, every time we divide edge of cube, right, into pieces, and we choose just one of them. So they're nested. They're nested. They intersect each other in the sense that, you see, they're nested. They intersect each other because, okay, I didn't understand correctly the former question, intersect each other. I thought it's about different cubes here, right? Different cubes do not intersect on when we divide in 2 power n pieces. We have okay, they intersect on side, right? Only. That is, but not common in the point. But it doesn't matter because we look at just one of them. In fact, maybe you have many, right? But we choose somehow just one of them, which is not covered by finitely many. That's main thing. Yeah. If C becomes a point of intersection, why did we denote it as a vector? Vector because this is in the set Rn, and we have an agreement to denote points of Rn as vectors. That's it. Okay, so now what was very important? Look, we have an open set. This is an open set, right? Which contains a point C. Now look, here is the point C. So this set is open, right? It means that there exists R positive such that neighborhood with this radius R is in our set J alpha naught. Let me draw the picture, right? So there exists a neighborhood which is inside our set J alpha naught. There is a neighborhood, right? Now look, that is here is R, right? R. Now what I want to prove that, look, C belongs to every cube, right? Lengths of edges tend to 0. They become smaller and smaller, right? So then it is clear, doesn't matter where is point C. The worst case if we have for a plane picture like that, right? This is worst case. I mean, C is a vertex of a cube, right? And I want to be sure that the whole cube is inside this neighborhood. When this is true? This is true when this side, look at this picture. So here we have d over 2 to the power m, right? 2 to the power m. So I want to choose such a large m that this distance diagonal of the cube would be less than r, right? Diagonal is square root over 2 times that one, right? That is for plane. And for Rn, the maximal distance inside hypercube is square root of n, right? Times the side. So if I choose m such that this one less than r, so choose m such that we have this inequality. Then what we have? Look, C belongs to our cube IM, right? And this cube is placed inside our neighborhood, right? So then IM is inside UR of C. That is the main point of our consideration. Look, so lengths of edges are smaller and smaller, right? So we can be sure that we can choose such a small length that the whole cube with this edge, if it contains C, and it contains C, right? C belongs to the intersection, right? So C belongs to our cube, and if we have such inequality, then for sure the whole cube IM is inside our neighborhood, right? Is inside our neighborhood. And our neighborhood is a part of G alpha naught, right? And what it means? So it means, look, IM is a subset of J alpha naught. IM is a subset of J alpha naught. But how we choose IM? Each of IM cannot be covered by finitely many of G alpha. And we covered it just by one. That is a contradiction. And theorem is proved. Yeah? So, I understand it's rather complicated proof, right? But you see, practically, yeah, I would say mostly you should use only logic, right? Little bit geometry, but mostly that is just logical. You should think logically. Okay, and as a corollary, let me write it down explicitly. That is called Heine-Borel lemma or theorem. Corollary. Corollary. Heine-Borel lemma in Rn. R1, sorry. R1, just R. Every covering of AB closed interval by open intervals has a finite subcovering. So if you have closed interval AB, right, and you have a covering by open intervals, doesn't matter how many open intervals you have, you can choose a finite subcovering. That is called Heine-Borel lemma. And in fact, the proof just, yeah, you see it. In fact, what we did, little modification for Rn, nothing else, because of this geometry. The inequality again, which inequality? The inequality is this inequality. Yeah, so once again, how this inequality appeared. I want to be sure that if C is a point of our cube IM, C is the center of this neighborhood, right? Then the whole cube IM is inside this neighborhood. That's it. So I need the worst situation is if C is a vertex, right? Then the largest distance inside the cube is along the diagonal, right? Main diagonal of the cube. So for 2 dimensions, that is the length times square root of 2, right? For 3 dimensions, you need to multiply by square root of 3, and so on. So for n dimensions, this is the largest distance between points of the cube IM, right? If this largest distance is less than r, then for sure the whole cube is inside our neighborhood, right? If it contains, that's it. Okay, I hope I explained. That's all for today. Thanks for your attention.